Okay, good morning and welcome to our second online lecture. So today we will talk about the two topics. So first of all, we will finish applications of factor groups and fundamental homomorphism theorem. So the first topic will be center and commutator subgroups. Commutator. Subgroups. And in the second part of our lecture, we will talk about the free groups, groups, and homomorphisms of free groups. Homomorphisms of free groups. Okay, so let's start with our first part. And let's talk about the center and commutator subgroups. So we will start by giving a definition. Sorry, no. Definition 1 of the center and the commutator subgroups. So roughly, this center and commutator subgroups, they would measure how far your group is from being abelian. So the center, so let G be a group. Let G be a group. Now the center of G, is the collection of the following elements. So we denote this set as Z of G. So this is the collection of elements Z in your group G, such that Z times G is the same as G times Z for all elements of your group. So in other words, this is the collection of all elements which commute with every single element in the group G. Now, it is a subgroup. It is a subgroup. And that was one of the exercises. So it is a subgroup of G. And that was one of the exercises in homework 2. Okay, so now the second part of this definition 1 would be as follows. So for a pair of elements, for a pair of elements, actually, because I'm running out of space on the blackboard, let me do the following. Let me break this definition 1 into 2 parts. And let's just continue on the next slide. So before, any questions about the definition of a center subgroup?
Yeah, just to make sure.
Yes.
If Z is some element in the center, that means that Z has to commute with every other element in G?
That's right. That's right. With every single element of G.
Okay, thank you.
So in particular, this implies that in principle, there can exist in a G, there can exist a larger commutative subgroup, which would commute between itself, but there will be elements which don't commute with every single element in G. So
okay.
In the definition of a center, we of course require that it commutes with every single element of G. Okay, so thanks for the question. Now today I don't have to save Blackboard, so I switch to the different applications and I just can scroll to the next slide. Yeah, here we go. Okay, so let's continue our definition. Let's say that this is definition 1a. So now let's define the commutator subgroup. So again, let G be a group. Now, with every pair of elements in G, we can associate the so-called group commutator. So for a pair of elements A and B in G, we can associate the so-called group commutator. The group commutator which I will denote by square brackets A, B with double line, and it's nothing as A, B, A inverse, B inverse. So that's an element of G. Now, the important thing to keep in mind here that how do I change? Sorry for this delay. Okay. The important thing to keep in mind here is that this group commutator is not the same as commutator of matrices. Commutator of matrices in linear algebra. That's a different thing. Linear algebra. Okay, so now once we have this group commutators, what we can look at, we can consider a subgroup generated by all possible group commutators. So the subgroup generated by all commutators. So that's a subgroup generated by all possible expressions as A, B, A inverse, B inverse, where A, B belong to G. It's called the commutator subgroup. It's called the commutator subgroup of G. Commutator subgroup of G. That will be our definition 1A. Note that it doesn't mean that all elements in this commutator subgroups are exactly commutators. We never said that. We just said that we consider a subgroup generated by all possible commutators. Okay, and in light of this, we will have the following lemma. So let me move on to the next slide. No. So our first lemma will be formulated as follows: that the commutator subgroup, C in G, consists precisely of all finite products, of all finite products of commutators. And the proof would go as follows. So let S be the following set. So this will be the set of all products of commutators, of all finite products of commutators, A1, B1, A2, B2, all the way to AK, BK. So that will be the elements of our set S. So here K is arbitrary natural number, and AJ, BJ are elements of a group G. Be the set of all products of commutators. So first of all, if we have a subgroup generated by all commutators, it definitely should contain S, right? So S must be a subset of C. Okay, so first note, S must be a subset of C. On the other hand, well, first of all, S is definitely closed under multiplication, right? Closed under multiplication. You just, if you have two finite products of commutators, you just put them right next to each other, you still get a finite product of commutators. And S contains identity. And that's because basically you can look at the commutator of identity with itself, right? So what it will be is E inverse, that's E, and that must be in S. And
okay.
Yes?
I just don't understand, for the group or for the set S, is it the set of all products of commutators, or is it the set
Yes.
of the commutators itself?
No. It's the set of all products of commutators. Thank you for the question. That's the most important part of what we're talking about right now. So we look at the set of all products of commutators.
Okay.
And we will prove that this set forms a subgroup. So that's an excellent question. Let me make a remark here. If you look just at the set of all possible commutators, then in general, this thing doesn't necessarily form a group because it will not be closed under multiplication. So if you have A1, B1, A1 inverse, B1 inverse, and A2, B2, A2 inverse, B2 inverse, no one said that their product will be again a commutator. And in general, it's not true. So in order to get a subgroup, you have to consider all possible finite products of commutators.
Okay, thank you.
So, thanks for the question. Any more questions so far? Okay, and finally, S is closed under taking inverse. Is closed under taking inverse. And to this end, let's look at the commutator. Let's look at the commutator. Let's say AB, and let's take its inverse. Okay, so what is that? That's AB, A inverse, B inverse, inverse. Okay, so we know that this is the same as BA, B inverse, A inverse. And that's literally as the commutator of BA. So the inverse of a single commutator is a commutator. Now, if you have finite product of commutator, of course, you're taking the inverse, that will still be a finite product of commutators. Okay, so altogether, this thing implies that S is a subgroup. S is a subgroup of G. And because we kind of proved that the commutator must contain S, and the commutator is obvious, the commutator subgroup is by definition the smallest possible subgroup which contains these commutators, then from here it would follow that S actually equals to C. So that's a subgroup generated by all possible commutators. A, B, and G. Okay, so any questions about this lemma? So this lemma essentially tells us the structure of the commutator subgroup. It allows us to describe explicitly elements of the commutator subgroup for any group.
Professor?
Yes?
So when you say that S, in the first bullet point, that says that S is a subset of C, right?
That's right.
Okay, so is the reason for that, like for S, do you also consider those products that consist of only one pair A1, B1, and is that why it's in
Of course.
C? Okay.
Well, no. So S is all finite products. Now we defined what is C. So let me comment on that. So what is C? C is a subgroup generated by commutators, right? So in particular, must contain commutators, and must be closed under products. Must be closed.
Oh, because it's a subgroup.
Yeah, under products. Now, altogether, this implies that it contains all products of commutators. Okay, does that clarify the?
Yeah, that makes sense.
Okay, thank you. So C for sure must contain all finite products of commutators. However, you have to prove that this is actually the smallest this set of all finite product of commutators forms a subgroup. Then it will be obviously the smallest possible subgroup, which contains products of which contains commutators, and that's precisely what we mean that this is a subgroup generated by commutators, right? So, any more questions so far? Okay, so now in the beginning, when I just start introducing these definitions, I said that in a sense, this commutators, this center and commutator subgroups tells you something about how far your group is from being abelian. So let's start with kind of this simple example. Example 1, which would go as follows. So every abelian group, has center as a abelian group, let's say G. So G has center of G. Okay, so what will be the center of G? That's the question to the audience. For a abelian group,
it would be all of G.
Yeah, that's right. Exactly, that will be all of G. And what will be the commutator subgroup?
the identity?
That's right. So the commutator subgroup will be a trivial subgroup. And that's precisely because if you take commutator of all pairs of elements in G, right? If you take commutator of all possible elements in G, A, B, A inverse, B inverse, it's E for all A, B in abelian group G. Okay, so now, and kind of if you have the direct product of abelian group with non-abelian, then sure enough, this abelian group will be in the center subgroup. Now, the story with the commutator subgroup is actually much more interesting. So let me probably mention dilemma, kind of dilemma 2, or better say, let's call it proposition, because it will not be used in the theorem. Proposition 1, Z of G is a normal subgroup. And again, because, yes?
Is this still when G is abelian, or is this general?
No, for a general group G. Well, when it's abelian, the statement is kind of boring because every subgroup, right, is normal. But this is true for general group G, not necessarily abelian. And the proof is kind of immediate. So let me just give you a sketch of the proof. I won't really go into details here. Sketch of the proof. Because Z in Z of G commutes with everything, then right and left cosets of Z of G must coincide. Okay, so that was easy. Now the story gets considerably more interesting with the commutator subgroup. So in a sense, the commutator subgroup tells you a lot about possible abelian quotient groups of your subgroup. And that will be actually the main theorem of this part of the lecture. So that'll be theorem 1. Again, let G be any group. And C in G be its commutator subgroup. Commutator subgroup. Okay, so then the statement has two parts. So the part A would tell us that C is a normal subgroup. Normal subgroup. And part B actually will tell us much more interesting story. So now let N be another normal subgroup, be another normal subgroup. Well, then the quotient group G mod N is abelian if and only if the commutator subgroup is contained in N. So it is a criterion for the quotient group of our group G to be in a billion. And that's why the commutator subgroup is important. So in particular, what this part B of theorem 1 is saying is that commutator subgroup is the smallest possible normal subgroup, such that the quotient would be a billion. Okay, so any questions about the formulation? Now let me briefly go over the proof of this theorem. Now I wanted, okay, so for the part A, first let's take C, D, and G be any elements in G, and we will prove the following identity. We will prove that if we conjugate the group commutator of C and D by G, then the result will be a product of commutators. So let's write this down explicitly. If we look at the G inverse commutator of C, D, and G, what we get is G inverse C, D, C inverse, D inverse, G. Okay, so we will break this product into two parts, D inverse G. So let's look at this guy and let's look at this guy. And between them, we will insert an identity. So G inverse C, D, C inverse, and let's just insert in between them an identity written in the following interesting form. So we will write it as G inverse, D inverse, D, G inverse. Kind of see that everything cancels here. D inverse, G. So this guy here is just an identity. Okay, now if we recombine the terms here, we can get G inverse C, D, C inverse, G inverse, D inverse, multiplied by D, G inverse, D inverse, G. And that's nothing but the product of two commutators. So the first guy is the commutator of G inverse C, G inverse C with D. And the second guy is the commutator of D and G. That's a nice trick to recombine terms here. Kind of, if you don't know that this is true, you probably wouldn't see it immediately, right? So, but that's okay. And of course, because this is a product of commutators, that belongs to C.
Shouldn't there be a G in the middle, not a G inverse?
Let's see.
G inverse C, D, C inverse G.
G inverse C, D, C inverse. Let's see.
So when you inserted the E, I think it should be a G, D inverse, D, G inverse.
Oh yeah, thank you. That's right. Where's the eraser? Thank you very much. Yeah. So I didn't insert an identity on the first place. Thanks. And now we're good. So because the inverse of that will be C inverse G. Good. Thank you very much. Okay, so now
Professor?
Yes?
For the second term, the commutator, wouldn't it be DG inverse?
DG inverse, thanks. Yeah, that's what happens when you hire. You actually spend more time correcting typos. Thank you very much. That's G inverse C, D, DG inverse. Good. Thank you. Okay, so now let W be the product of commutators. Let's take C1, D1, right? Multiplied by the commutator C2, D2, multiplied by the etc. by the commutator, say Cn, Dn. So be a finite product of commutators. Product of commutators. So what do we get here from equation star? From equation star, we conclude that if we conjugate this W with the element G, then this is the same as G inverse C1 D1, right? G all the way. Well, let's put the second one. G inverse commutator C2 and G2, G all the way to G inverse commutator of Cn, Dn, G. And it must belong to C. So this guy belongs to C, this guy belongs to C, this guy belongs to C, so their product also belongs to C. G inverse WG belongs to C. And that was exactly the criterion of a normal subgroup. So we take any element of C, right? And we prove that G inverse WG is in C. So C is a normal subgroup. Well, subgroup. Here we go. Okay, so any questions about this proof? So now let's move on to the second part of this theorem. So in the second part, let's first prove that if C is contained in N, then it implies that G mod N is abelian. Now here, let's look at the multiplication. So elements of the quotient group are exactly cosets, right? So we can look at the multiplication of the coset containing A and the coset containing B. Now this will be the coset containing AB, because N is a normal subgroup. And now what can we do? We can do the following thing. We can look at this AB. Now because A is the same as, now what is N? So N is the same as the coset containing any element of N. So for example, we can look at the commutator of B inverse, A inverse N. So this guy in the brackets is just exactly N. So this belongs to N, and this whole thing equals to N. Okay, but now if we write this down explicitly, what do we get here? We get AB, B inverse, A inverse, A, B, N. Well, we can cancel these guys, and we can cancel these two guys. So this is the same. Oh, wait a second. BA. Again, I hurried and I messed up the calculation. So BA. And what we just proved is that this is the same as BA. is the coset containing BA. There's the coset containing BA. And that's, of course, the product of these two elements in a different order. A and so the quotient group is abelian. Quotient group is abelian.
Professor?
Yes.
So to demonstrate that specifically a quotient group is abelian, you just show that multiplication of any two cosets is independent of the order?
Yes, exactly.
Okay.
Well, because these cosets are exactly elements of the quotient group, right? This is how we define the quotient group.
Okay, thank you.
Okay, so now let's prove the other part. So let's suppose that G mod n is abelian. So now G mod n is abelian. And let's conclude from here that C must be in n. To this end, let's look at the following. So let's look at the group at the coset. So let A, B, B, and G. And let's look at the coset containing their group commutator. The coset of n containing their group commutator. Now this is the same as A, B, A inverse, B inverse. So as the coset containing A, B, A inverse, B inverse. And now because we know how the multiplication in the quotient group works, this is the product of the following cosets: A n, B n, A inverse n, B inverse n. And we know that G mod n is abelian. Now we will use that. Here to reorder the elements in this product. So we will move the coset containing A inverse n right next to the AN, and we will move the coset containing BN right next to the coset containing B inverse n. And of course, this is the same as the coset containing AA inverse n multiplied by the coset containing BB inverse n. Both are actually the cosets containing an identity, and that's an identity in the quotient group. Now, what we proved that the coset containing every single group commutator is the same as n. So this implies that this group commutator AB is in n. And because every single group commutator is in n, then the subgroup generated by them must be a subgroup of n. Okay, so that concludes the proof of the theorem. Okay, so any questions about the proof? Now, what is most interesting is the corollaries. So let's talk about the corollaries of this theorem. They are actually quite striking. So, corollary 1. Now let G be a simple non-abelian group. So let G be a simple non-abelian group. Both requirements are actually important here. Then the commutator subgroup, C. So what should be the commutator subgroup? Any suggestions? So we kind of already learned that the commutator subgroup is normal, right? It cannot be a trivial subgroup because G is non-abelian. And the only two normal subgroups of a simple group are either trivial or the entire thing. So C actually must be equal to G. So then the commutator subgroup is the entire thing. Proof. C is normal, and C cannot be a trivial subgroup because G is non-abelian. And now, since G is simple, the only non-trivial normal subgroup is G. Here we go. And here an example. That will be example 2. Commutator subgroup of AN. Commutator subgroup of AN is entire AN for n greater or equal to 5 when this subgroup is simple. Oh, when this group is simple. Now let's look, let's have a closer look at the permutations group. Consider Sn. Yes. Okay, so consider Sn for n greater or equal than 5. So what do we have? We have the quotient group Sn over An isomorphic to Z2. In particular, this quotient group is abelian. In particular, it is abelian. This factor quotient group is abelian. Well, from here it follows that the commutator subgroup is in An, which is a subgroup of Sn. So, so when n greater or equal than 5, An is simple. An is simple, which implies that the commutator subgroup actually equal to the An. Here we go. So that's what we can conclude about the commutator subgroups of the permutation groups using this theorem. So any questions so far? So that's basically everything I wanted to say about the center and the commutator subgroups for now. So then let's move on to the second part of our lecture, which will deal which will be about free groups and homomorphisms of free groups. Free groups and homomorphisms of free groups.
Professor,
Yes.
today's lecture, does that correspond to section 15 of the textbook?
It's 15, and well, the first part is section 15, right? It's what left from the previous lecture. And this material about the free groups and homomorphism of free groups is the section 39.
Okay.
So last time we didn't have time to finish this commutator and center subgroups. So that's why we're talking about this today. Because apparently writing on the graphic pad takes slightly more for me than writing on the blackboard. And we're slightly behind the schedule, sorry about that. Okay, so let me put it here. So this is paragraph 39. Don't be afraid of the number. It's actually, the reason it's not right there is because the subsequent material of the ring theory would not rely on the free groups. Yet many of your subsequent math courses would talk about free groups and would talk about group presentations. That's why we will go into this sections 39 and 40. Okay, so let A be any set, not necessarily finite or even countable, necessarily finite or even countable. And we will denote the elements of this set as A sub I, where I runs over the indexing set. So we will call A the alphabet. So we will call A the alphabet, and elements of this set, AI, the letters. Now we say that a word well, in alphabet I, that A, W is just formal collection of symbols. AI1 to the M1, AI2 to the M2, all the way to AIK to the MK is a finite string consisting of symbols A, I, L to the ML. So here IL belongs to our indexing set. So this labels the letter of our alphabet, and ML is just an integer number. And ML is integer. ML is integer. Now, here is the couple notational remarks. So we think of a letter AI can be thought as a word. Namely that's AI to the 1. So this ML will have the meaning of powers. So with every letter, we can associate a word, AI to the 1. And finally, the empty word, is denoted by symbol 1. Is denoted by symbol 1. So empty word meaning that there is no, this is empty string. Okay, so any questions so far about the alphabet and words? So now let W denote this, the collection of all words. Let, and I will use calligraphic W, denote the collection of all words. We can define a binary operation. Define a binary operation. Let's say it's star from W cross W to W, which just takes a pair of words. Just takes the pair of words W1, W2, and puts them right next to each other. W1, W2, where the result is simply a concatenation of words. Concatenation of words W1, W2. Now, in immediate facts, you can notice that concatenation is associative. Concatenation is associative. If you take W1, put it right next to W2, and put W3, that's the same as if you first concatenate W2 and W3 and then put them after W1, right? And that empty word is an identity. Word is an identity. However, this W with the binary operation star is not yet a group. And the problem is, of course, with the inverse. And where's the red pen? Oh, no. However, this W with the binary operation star is not yet a group. And the problem is that there is no inverse for a non-empty word. Not yet a group, because the only invertible element is empty word, word 1. And however, we can remedy the situation, but we can remedy the situation by considering equivalence classes of words. Equivalence classes of words. That's what we will talk about on the next slide. So, any questions so far?
Yeah, I was just wondering, why is 1 the only invertible element?
That's a great question. So suppose you have non-empty word. Suppose you have non-empty word.
Okay.
Suppose W equals to, I don't know, A1, A2. Now, what possible word you can put on the right so that the result will be an empty string?
It'd be,
With this, what?
I would say it would be A2 inverse, A1 inverse.
That's a great question. That's a great remark. But we never said that the word A1, A2. Okay, so let's say that this was W1, W2, A2 inverse, A1 inverse. But we never said that the result of this binary operation A1, A2, A2 inverse, A1 inverse equals to 1, right? Because this is a string. This is how we define the collection of all possible words. This is not an empty string, right? And in order to say that it is equals to 1, we need to define operations on the string. And these are called elementary contractions. Namely, we want to say that the string with A2 and A2 inverse staying right next to each other is the same as the string just with nothing there. So that's a great point. Thank you very much.
Oh, so just to confirm then, the reason why W2 is not an inverse of W1 is because we never defined inverses for each individual element.
Well, we never thought of this kind of strings as powers of some elements yet.
Okay, that makes sense.
So that's exactly what we're going to do on the next slide. Thank you. Okay. So now definition 2. Definition 2. So we say that the two words are equivalent. We say that the two words W1, W2, and this W are equivalent if they are related by sequence of elementary contractions. Sequence of so-called elementary contractions or elementary expansions. Expansions of the two types. So the first type 1, is when we have some word which contains an element aj to the 0. We want to say that it is equivalent to the word where we just simply dropped this aj to the 0, right? And type 2 if we have a word which would contain a j in M and a j in N right next to each other, we want to say that this is the same as the word containing a j. Oh, W2, we want to say that this is the same as the word containing a j to the power m plus n, W2, right? So this kind of two types of elementary contractions. Now, if this kind of letters would be generators in some group, those two operations you would obviously see on the words in generators. But now AJ are letters, that's why we have to impose these relations manually. We have to say that the words where we have AJ with 0 is the same as just dropping this AJ to the 0, and when we have kind of two powers of the same element next to each other, then this is just AJ to the m plus n. Okay. So let's look at the example. So alphabet, let's take finite alphabet. I know 3 of them will be enough for now. And let's look at the following word. So A1 to the 5, A2 to the 7. Now we want to say that this is the same. This is the same as the word A1 to the 5, A3 to the 0, A2 to the 7, right? And that's expansion of type 1. On the other hand, using expansion of type 2, we can also say that this is the same as A1 to the 5th, A3 to the -2, A3 squared, and A2 to the 4th, A2 to the cube, something like this. Okay. Now we have certain operations, and we can consider equivalence classes. So now we can consider equivalence classes of words. This is W modeled by this relation tilde. And however, a priori, no one guaranteed that, our concatenation, we define like the binary operation of the set of all words, gives us a good operation on the equivalence classes. But this is actually true. And that will be the statement of our lemma 2. So lemma 2. Oh, sorry. Forgot. This is a good place to introduce the so-called reduced words. So definition 2a, kind of in this example, you see that the expression on the left is kind of the simplest form in which you can write the simplest representative of this equivalence class. And this motivates the following definition, that we say that a word W is reduced if we can make no further elementary contractions. Make no further elementary contractions.
Professor,
Yes.
what does it say next to equivalence classes of words? It's like W mod something.
Yes. Mod this equivalence relation tilde.
Oh. Okay.
Okay. So for example, this guy is reduced. And these are not reduced. Now, the good thing about it is we can now describe this equivalence classes explicitly, because in each equivalence class, there is a unique reduced representative. So you kind of already familiar with that, that if you have a set, you have an equivalence relation, right? It partitions the set into equivalence classes, but in general, it's quite hard to describe what equivalence classes are, right? Now here, we can describe equivalence classes by looking at reduced words. So our lemma 2 would be as follows. Lemma 2. First of all, by a sequence of elementary contractions, we can bring any word. We can bring any word W to the unique reduced form. And we will denote this by a row of W. Now, the second part of this lemma, if W1 equivalent to W2, in the sense of definition 2, then their reduced words must be literally equal to each other. And finally, the most important part of this lemma 2 is that whenever we have W1 equivalent to W2, this implies that the concatenation of W1 with W3 is equivalent to the concatenation of the W2 with W3. That's for all words W1, W2, W3. Now, in other words, concatenation is well defined on equivalence classes. Concatenation is well defined on equivalence classes.
Professor?
Yes?
That's the last bullet point. Wouldn't that only work if you define, or rather if you verify cancellation laws as you would in a group?
That's right. So that would be precisely the proof. So
okay.
Wait a second. So this is not the same as cancellation laws in a group. Sorry, I misunderstood the question. We don't have a group yet, right? Instead, we have the collection of all words, and we have an associative binary operation on the collection of all words, right?
Yes.
Now, if you define equivalence classes of words, now and say that your associative binary operation kind of plays nicely with these equivalence classes. And that's precisely what we need to prove in the last bullet point. We need to prove that if we take two equivalent words and multiply them by some other word, then the resulting words will be equivalent.
Okay, that makes sense.
So we don't have any group yet. Of course, in the end of the day, we will define the group, which will be called free group. And thanks for the introduction to that. And of course, the cancellation law will hold there, right? And kind of this expression here would make perfect sense, right? But so far, we don't have any group, right? Okay. But that essentially precedes our theorem / definition 2. Oh, so, it's 3 already. So theorem / definition 3. That this W with a binary operation, that the set of equivalence classes, the set of equivalence classes W modulo this relation tilde, together with the binary operation star, forms a group. We denote this group, by f of A, and say that it is a free group. It is a free group with alphabet A. Okay, so proof. First of all, by last part of lemma 2, the binary operation star is well defined on the equivalence classes. Is well defined. Now it is also associative and empty word is an identity element. Word 1 equivalence class of empty word. Equivalence class of empty word. an identity. But most importantly, now we have inverses. So if you have a word, which let's say a1 to the power m1, ai2 to the power m2, all the way to aik to the power mk, then W inverse can be taken as a word, as an equivalence class of the word, which is aik to the minus mk, aik minus 1 to the power minus mk minus 1, all the way to ai1 to the power minus m1 is an inverse to W. And that's because now we can make contraction move, right? So if we take W inverse, that will be AI1 M1, AIK MK, multiplied by AIK minus MK, AI1 minus M1, and that's equivalent to an empty word. Here we go. Okay, so any questions about the definition of a free group? Now let me announce what we will be talking next time. So why do we call these groups free? And the reason for that is because there is no restrictions. There is no, because there is no relations between generators which are letters of the alphabet met. And in addition, if you have, okay, so we have this A, right? This A is a subset of a free group generated by A. Now, suppose you have any map phi to any given group. And the point is, there exists a unique map, let's say phi capital, which is a group homomorphism from the free group to G. In other words, any function from the alphabet to any other group defines a homomorphism of a free group. There exists and unique. Okay, and that's what we will prove next time. Prove next time. Okay, so that's a good place to stop for today. So do you have any questions so far?
Yeah, I was just wondering, what's the reason why the center is called like the center? Like, why is that the name given to that subgroup?
That's kind of, there is also standard notation for the central element, which commutes with everything, and that's probably the kind of center subgroup is the collection of all central elements.
Okay.
I cannot say more about the history. I'll probably look this up after your question and probably can tell you sometime later. Okay, so any more questions so far? Then I will stop this session and I will save the video and I will come back in a few minutes with office hours.